Right, it's recording. And just in case something happens, I've got an alternative recording method and I'll start recording on that one. And there we go. All right, let me go ahead and pull up my whiteboard. And there it is. Alrighty, so where were we last time? Last time we were doing these things such as I don't know, we were putting together molecules like SF4, for instance. And how will we, yes, go ahead.
Can you share your screen?
Oh, thank you so much for reminding me, because if you don't tell me, then I will sometimes forget. Thank you so much. Everybody see the little girl? All right, wonderful. Let me go ahead and start sharing again. Thank you so much for letting me know, because if you let me, I'll just go blah 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 blah. I'll just go on and on and on. All right, so all right. So this is kind of like where we are. Now, let's say we take sulfur tetrafluoride and we want to know what's the Lewis dot structure. We should be able to do that. And what's going to happen between these two chapters, 8 and 9, I believe this is 8 and 9, yeah, is that we'll start with this. We'll start with SF4, or we'll start with CO2, or we'll start with, I don't know, bromine tetrafluoride ion or something. And we will be able to answer a series of questions. Well, yeah, a whole bunch of stuff off of just this innocently looking formula up here. All right, all of this stuff comes from there. So one of the first things that we need to be able to do with this is we need to be able to name it. Let's name this. So we have sulfur, tetra, tetra means 4, right? Fluoride, sulfur tetrafluoride. Okay, so we can name this. This is one of our skills, right? And we can take a look at the individual bonds. Let's see the SF part. And we can say, you know what, that the bond, this is a polar bond. We can say that, okay? All right, why is it a polar bond? Because it's from different parts of the periodic table. From a simple standpoint. From a more technical standpoint, they have different electronegativities, so you have a net debye across the bond. So we can say something like that. And then we can say things like, you know what, I wonder what the Lewis dot structure looks like. And so we look at the number of valence electrons for each one. Sulfur has 6. We look on our periodic table, we count across 1, 2, 3, 4, 5, 6. We get the sulfur. We look across the periodic table, we look at fluorine, and we see there's 4 times 7, which gives me 28 valence electrons. Okay, sound familiar so far? Okay, this is what I mean. I'm running through stuff that I can say from this little formula. And so I add these guys up and I get 34 valence electrons total. And what else do we know about this? What do we know about this 34? It's not the total. It's not all electrons. In other words, it's just the valence 34 valence electrons total for the whole thing, right? And then we say, you know what? I'll put this sulfur in the middle. I'll put those fluorines at north, east, south, and west. And oh, by the way, if you have others, you're going to put them in there too, right? And by the way, we have a lab that's going to be due Saturday, and this is what you're going to do for that lab. And so we go ahead and I have 34 electrons to play around with. 34, I have 34, no more, no less. And we go 1, 2, 3, 4. I used 8, right? Minus 8, and I get, what is that? That's 26 left over, right? By the way, while I'm doing this, and I'm gonna make an aside on here. This is a what do you call a style sort of note. Now I meant to say something last time. I kept meaning to say something. Do you see how this is orientated? You see that? You see those dots? You see how that's orientated? I'm just talking about orientation. That's all I'm doing with these blue dots. See how that is? Do you see how these dots go that way? Okay, please do that. Do not do this. Do you see what I just did here? You see how that's orientated like that? Don't do that. All right, don't do that. It's a style thing. I've seen folks do it. I've actually seen it online too. It's not illegal. It's not illegal. It's just ugly. All right. All right. I want to live in a world where everything's pretty. All righty. So let's see, minus 26. So I got so I just did 8 and I have 26 left over. I have room for what? I have room for 6 more. There's 4 of them. That's 24. So I'll go ahead and put 24 up there and see how you see the direction I'm putting them? See those blue arrows? It's a style thing. I meant to say something about it last time, but I didn't. And so I go ahead and put these guys on all the way around. Okay, and don't skip steps. If you do, bad things will happen. And so 6 times 4 is 24, so we go minus 24. Leaves me 2 extra. Okay, so far so good. I've got them all accounted for. 34 minus 8 is 26. 26 minus 24 is 2. I have 2 left over. Where are we going to put those 2? We'll put them as lone pairs. We can put them anywhere you want. You know what? I'm going to, just because I want to be different today, I'm going to put them over here. Why not? I could have put them anywhere I want. And now I'm going to go ahead and circle these guys. Now I know I do red for mean don't be this person, but I'm doing red just to show a different color this time, okay? So let me erase this up here. Let me go ahead and put these 2 blue dots back over there. And there it is. And so we've got minus 2 gives me 0 left over. And so this is an example of what was this? This is a hypervalent, which just means that it violates the octet rule, which is not much of a rule at all. All right, and of course the explanation is of course they have expanded D levels, and I already told you that probably it's more of a steric sort of thing. Steric means that it takes up volume, and it's just that it's got more room. You just got enough room. Okay, and so we have all of this, and we have this molecule, and there it is. Now, I'm going to caution you on this. This does not tell you the geometry. The geometry is coming up. This is just a start as far as a representation. What's the purpose of all of this? I'm just going to write down a purpose here. The purpose of these Lewis dots, Lewis structures. Okay, the purpose of these Lewis structures is one is to get bonded lone pair. That's one purpose. Because to be able to do the geometry, which we're about to do, you need to know how many bonded you have and how many lone pairs you have. How many bonded do you have here? You got 4 bonded and you have 1 lone pair. Okay, so that's something that we need to know. That's the purpose of this Lewis dot. The other purpose that we're going to get is to get something called formal charges. All right, that's going to be other purpose that we're doing this. In case you're wondering why are we going through all this trouble besides just producing pretty pictures. This is where we're heading with this. Okay? This is where we're heading with this. All righty, so we're able to do the Lewis dot structures. Okay, so now we need to finish out the chapter. All right, we're going to shift gears momentarily, but we're going to come back for chapter 9. We're going to come right back to this. All right, just understand, we're not stopping with this. We're shifting gears momentarily just so I can finish chapter 9. All right, so bond enthalpies. Now, if you remember, what's an enthalpy? That's delta H, right? And it's some sort of energy. That's an enthalpy. And you remember what I said about delta H at the beginning of chapter 5? I said, you know what? There's a delta H for everything. Well, there's a delta H for something called bond enthalpies, which is basically the energy to break a bond. Okay, that's what it is. It's the energy to break a bond. Okay, and there are bond enthalpies for all sorts of things. And I will tell you first off, we're going to say that the bond enthalpy, for instance, for a carbon-carbon bond is 348 kilojoules, and I believe it's in per mole, and it is. And that's for a carbon-carbon bond, all right? Not important that you know the number. I'm just saying that there is a number that goes with this, okay? And if you have a double bond, it's 614 kilojoules per mole for a double bond. And look at this. Look at this right here. Would you say this is about twice as much? And it is. It is. 600 and some change is almost twice as much as 300 and some change. And if you go with a triple bond, you get 839 kilojoules per mole for a triple bond. And if you look at 800 and some change versus 300 and some change, I would say that if you squint your eyes just right, it's about 3 times as much for the energy. Almost thereabouts. It's in ballpark. And so this is one of the things that actually makes sense in chemistry, that if you have 3 times of something, everything else should be 3 times as much. And at least for the bond enthalpies, this is true. However, for bond lengths, how long, the length, and this is times 10 to the minus 10th meters, by the way, that's something called an angstrom. And it goes, just in no particular reason, 1.54 angstroms. And this is 1.34 angstroms. And this is 1.20 angstroms. An angstrom being 10 to the minus 10th. An angstrom is 1/10 of a nanometer. It's an old unit. It's used because it gets you numbers like 1 and 2 and 3 if you go times 10 to the minus 10. That's the only reason why people use angstroms. It's a non-SI unit. It's a non-engineering unit as well, because it's not a multiple of 3 as far as the exponent goes, but it's a pretty common one to use. Now, if you look at these, what do you see here though? You see that as the bonds get stronger, because that's what these enthalpies mean, is the bond strength, the bonds get shorter. And this should make sense as you have these two atoms being pulled together. And I'm just not, they're not, I really should have put a C down. I meant these are balls. These are carbon balls. Let me put a little C in there. Carbon atom, carbon atom. Let me put a little C in there. Okay. So these are carbon atoms. And they get shorter, but you know, think about it. If you think about a bond as being kind of like a spring, you know, and it's stretchy, these guys do bounce back and forth. This is like having two springs. This is like having 3 springs, you know, and if you got more springs, it's going to pull them together stronger. And so it gets a little bit shorter, but the point I'm making, besides that they're getting shorter, is it's not 3 times shorter. All right, the bond length here for a triple bond is not 1/3 the bond length of a single bond. Okay, so the only thing that's increasing by factors of 3 for a triple bond is the bond energy. How much energy does it take to break that triple bond? Okay, that goes about 3 times as much. As far as bond length, it's just a smidgen shorter. It's measurable. 1.5 versus 1.2, you can measure that, but it's just a little bit shorter. Okay, but they do get shorter. Now, what do we need to do with this? Do you need to know these numbers? No. You don't need to know these numbers in the sense of, do I need to memorize them? But you do need to say a single is longer than a double, which is longer than a triple. Or you can say a triple is shorter than a double, which is shorter than a single as far as length goes. All right. And you should be able to say, the bond enthalpy as you do this here, as you double the number of bonds, it should double the energy. Okay. This is generally what, now, as far as these numbers go, you look them up. You look them up. These kind of numbers have been figured out a long time ago. So you just need to know where to find them. That's what you need to know, is where do you find these? Now, where do you find these? Well, the bond lengths you find on page 329. This was on page 329. And bond enthalpies you find on page 326. So this was page 326 for this stuff. Okay, this is where you find this stuff in this textbook, or you just go to Google and you look it up. What's the bond length for a carbon-carbon bond? And it'll tell you. Okay. Now these numbers will differ a little bit depending on whose table you're looking at. It's the way it goes. These are experimentally determined numbers. There's some error bars associated with them. Now, what are we going to do with this besides just saying, you know what? Oh yeah, Mr. Pierce. Oh, a triple bond is about 3 times stronger and it's a little bit shorter. Okay, good. This is important though. I mean, it's a hand waving sort of thing, but yes, it is important because it has real world consequences when you're looking at real molecules. Okay. All right. So what are we going to do with these bond enthalpies? And here's what we're going to do is we want to be able to calculate delta H for a reaction. And so far, we've had several different ways of doing this. We could measure it experimentally. We could say, the combustion of methane in oxygen to make CO2 and water, we got 800 and some odd kilojoules, right? All right. And that was just given to us. And we could use Hess's law, where we have to take a series of equations and manipulate them, flip them, multiply them, whatever, and we get a value for delta H reaction that way, right? And then we had yet another way of getting at delta H reaction, which was we had our enthalpies of formation. And then it's products minus reactants gives us kilojoules for the reaction, right? As long as you have a list of all the components of the reaction and delta H is a formation, you can get a delta H reaction out that way. And now we have another way of getting at the same number using bond enthalpies. And this would be the sum of bonds broken minus the sum bonds formed. Bonds broken minus bonds formed. So this is just another way of getting at the same number. So we have, let's see, we've got, just measure it, that's 1. We've got using Hess's law, that's 2. We've got enthalpies of formation, that's 3 different ways. Now we have a 4th way of getting at the same number. And you can do all 4 and you'll get 4 different numbers. They should be close, but they'll be 4 different numbers because you have 4 different ways of doing it. Now, these bond enthalpies on page 326, they represent averages. Because a double bonded carbon, the energy to break that bond depends on the molecule it's in. It depends on the things that are also attached to it. They do make a difference. Now, a double bond is going to, how much is a double bonded carbon? Is 614. Well, in one molecule, it might be 620. In another molecule, it might be 605. On average, it's 614, okay? And it gets you close enough. It gets you close enough. So let's look at a reaction. Now, to do this, you have to be able to sketch out the molecules themselves. All right. And so what I want to do, let's just do one just for the hell of it. Okay, look, here's a reaction. I'm just going to put one down randomly. Let's figure out what delta H reaction is for this. And so I'm going to say, let's do the combustion of methane, which is what happens in a Bunsen burner. And we're going to say plus oxygen. And we're going to get carbon dioxide plus water. All right, and we have to balance this. So this would be 2 and 2 right there. Okay, so we have our balanced equation. And I want to know what's delta H for this guy. Okay, so how are we going to do this? Well, first off, we have to do this. We could go measured experimentally, and the number is well known. We can use Hess's law. We've done this. Or we can use delta H as a formation. We've done this. Or we can do bonds broken minus bonds formed. And so the first thing we have to do is we have to be able to know what the molecules look like. This is also another reason why we do our Lewis dot structure, so we can decide what do they look like. And so what these look like is like this. Here is a carbon with 4 hydrogens, and they're attached. And then we have 2 of the oxygens, and they look like this. They're double bonded, and I'm leaving off the extra electrons. All I'm interested right now is just the bonding. And we got 2 oxygens, and then it goes to carbon dioxide, and carbon dioxide looks like this. It's double bonded oxygen, double bonded oxygen. I don't remember if we did this last Monday, but if you can do this Lewis dot structure, you'll see the carbon dioxide is a double bonded oxygen once you do everything. And then you've got 2 of these waters, and a water looks like this. HOH, there it is. And you got 2 of those. So I sketched these out so that we can see what the bonds are. So we can classify what's been broken, what's been formed. Now, I'm going to go ahead and just move this up a little bit. Okay, I'm going to move it up a little bit so we can work here. And so what we need to do is look at bonds broken. Now, everything on the left-hand side, these guys, these are where you find the ones that are broken. I think that should make sense, right? You got to break them, you got to form them, you know? And everything that's going to be formed is going to be on this side. Now, they're not necessarily broken from one side to the other, and they're not necessarily formed from one side to the other. All right, you could just break one and form one. Now, I think on this one, we're going to break everything and we're going to form everything, and it's not always that way. Okay, it's not always that way. So let's go. So what I like to do is I like to break this up. I like to break it up. I like to break it up into 2 steps. I like to add up everything that's broken. I like to add up everything that's formed and then subtract it instead of trying to do one big formula. That's just the way I do it. You can do it one big. Just be very careful about signs. Remember when we did bond enthalpies of formation, and I said, yeah, better use lots and lots of parentheses and be very, very careful about those minus signs. So it's the same sort of thing. If you're going to mess this up, usually it's signs, because you're taking a minus of a plus and whatever. Okay. All right. So what do we have here with broken? Well, I'm going to go from this carbon-hydrogen bonds, and it doesn't look like I have any carbon-hydrogen bonds on the right-hand side. So that means they all have to have been broken, because they didn't survive going through the arrow. Okay, so we have carbon, so I'm going to say broken. I'm just going to make a little table here. I'm going to say broken, and I'm going to say carbon, hydrogen. Okay, you see what I just did? I'm just making a list, the running total. And I look on my table on page 326, and I see carbon, hydrogen is 413. And these are all in kilojoules per mole. Okay, I'm not going to put any units down because it's understood that, and it's 413 according to the table. Now, How many carbon-hydrogen bonds do we have, though? We have 4. There are 4, and I'm going to put it in blue here, 4, because there are 4, see, arrows here, arrow, arrow. There are 4 carbon-hydrogen bonds. You see that? There's 4 of them. And so I'm just going to go ahead and add it up. What the heck? Let me grab my calculator here. And 4 times 413, 1652. All right, so I have those carbon hydrogens. Now I look up here and I see that there are oxygen, double bonded oxygen. Do I see any of double bonded oxygen on the right hand side? And I don't, which means they had to have been broken. You got to ask yourself this question every time. Because if it hasn't been broken or hasn't been formed, you should just ignore it. All right. So it looks like I've got carbon. It looks like I've got carbon, hydrogen, and now I have oxygen, double bonded oxygen. Okay. And each double bonded oxygen, I look on page 326, and I see 495. But how many do I have? I have 2. There are 2. See? 2 of these guys. See the 2? And that is, and I could do this in my head, but I'm not going to. 2 times 495, 990. All right. Is there anything left to break on the left-hand side? And the answer is no, there's nothing left to break. Let's go ahead and add these guys up, because that's what it means. The sigma means to add them up. And so we go 990 plus 1652, 2642. Now this is bonds broken. We have to put energy in. Bonds formed, we're going to subtract off. So now we've done broken, so let's do formed. So we go formed. And once again, this is in kilojoules per mole. Okay, and we're taking this, all of this is coming from page 326 out of your text. All right, and if you're using a different text, it's just, you need to just find it's on a different page. That's all. Okay, bonds formed. What do we got here? Well, I like to work left and right, left to right. I see C, double bonded O. Now, I look on my chart here and I look for carbon oxygen single bond, and that's 799. But how many carbon double bonded oxygens do I have? I have 2. And there's one. And there's the other. I have 2. And there are no others. Now keep in mind, one thing that's real easy to make a mistake on here, and it's really easy to make mistakes on this because you have to go through this very carefully. Make sure that it doesn't appear in more than one spot. Particularly things like hydrogens, you know, they have a tendency to be everywhere. So you just got to be careful. Okay, but in this case, carbon double bonded oxygen, there are 2 of them because carbon dioxide has 2 of them. All right, and so we'll go ahead and multiply this out, and it should be 1600 minus 2, which would be 1598. And I'll make sure that's right, but I just did the math in my head, and sure enough, it is right. Okay, and we've got that, and now we have these OH bonds. You see the OHs on the waters, there are 2 of them. OH. But what? We have 2 of everything up there. You see that? It's 2 of everything. If there's 2 OHs for each water molecule, all right, very important. 2 OHs for each water molecule. But how many water molecules do you have? You have 2. So that means there's 4 OHs. There's 4 OHs up there. And we look on our table and we say OH, and I see 463. And that is times 4. Okay, because there are 2 of them here, but then we have 4 altogether. Everybody with me so far? All right. You see that, right? That, you said you have each water molecule has an OH. All right, and then there's 2 of them. Okay, so that makes 4 altogether. And so let's see, 463 times 4. 463 times 4, and I get 1852. All right. And hopefully, if I haven't made a silly mistake, and it's really easy, and I make mistakes. Don't get me wrong, I make mistakes. Just ask my wife. I make mistakes every day. And so you can make mistakes on this, and if you're going to make a mistake, it's just going to be something silly. It's going to be, I just missed something. You know what I'm saying? It's easy. There's just a lot to keep track of. But anyway, let's go ahead and add them up, because that's what it means to be a sum. So we take our 1852 plus our 1598, and I get 3450, and that's kilojoules per mole. Okay. Now what? And this is the reason why I'm doing this step by step and individual step instead of trying to lump them all together in one big formula, is because it's easier to keep track of this way. Okay, so I've broken all the bonds. I've formed the bonds. Now what do? Well, it's broken minus formed. We take the difference between the two and we say 2642 kilojoules minus 3450 kilojoules per mole. I take the difference, 2642, and then I subtract off my answer, and I get minus 808 kilojoules per mole. And so delta H for the reaction of CH4 plus two oxygens, which gives me a carbon dioxide, plus 2 waters. What we're going to say using this calculation is we're going to say that delta H of reaction for this thing is minus 808 kilojoules per mole. All right, now I don't know what this is off the top of my head, but let me look on, I'm going to look this up. Let's see. First off, I've got 2 messages. Let's see. So I'm going to look this up because, Google's a wonderful thing, right? Google's a wonderful thing. So I'm going to look up on Google, and I'm going to say heat of reaction for methane. Let's see. Oops, heat of combustion. So we're going to do heat of combustion. It's much faster if I just use combustion methane. And combustion releases energy. 802. So the experimentally determined, the experimental number is 802, minus 802 kilojoules per mole. How about that, guys and ladies? How about that? See, when I look at that, and I see 802 is what if I actually went out and I had to set up an experiment and very carefully do this. But if I just had a table in front of me and I got 808, what's the percent agreement between that? Hey, that's something out of our labs, isn't it? Percent agreement. So we say that's 6 divided by 802 times 100. That's 0.7%. 0.7%. That's pretty good, don't you think? That might even be good enough for an industrial facility where you're making millions and millions of pounds of stuff a day. Might be good enough, 0.7%. So to me, this is a wonderful thing. You don't have to necessarily go do an experiment. You just look it up in a table. Even for a reaction that you've never seen before. Now, we've seen methane, burning, and that's a Bunsen burner, okay? But that's the point of doing these things. Do you see what I'm saying?
Can I ask a question real quick?
Absolutely. You go right ahead.
Why is it that the energy for formation is not written as a negative?
Oh, okay. Because it is.
Just eventually it becomes a negative
Yeah, yeah,
in the
because
formula?
exactly. Because really what you're doing is a Hess's. You're saying energy to break it, and then you've got energy to form it, right? This is what we're doing, and then you're going to add them up. And so coming down is negative, going up is plus.
Right.
Okay, and the amount and the difference in energy between the two, that's your delta H reaction. So from a strictly mathematical standpoint, it does become negative. It is negative because it's it is right here.
Once it's plugged in.
Once it's plugged in, it becomes negative. So the energies that you see in the table are all for breaking the bonds. The table is all for breaking. When you say bond enthalpy, we say how much energy to break it. Well, if you break it, you actually get the same amount of energy back, and you change the sign. What did we do here? We changed the sign, and then we
Okay.
add them up. Okay, so yes, you are absolutely right. What happened to the negative sign? It's there. It's there. It was there all along.
So it's kept tripping me up on the problems, working the problems. I kept using a double negative and getting a positive. So
Uh-huh.
these values are to be used in that formula.
As
It,
they
it,
are in the table.
okay, but if we were just talking about if you just asked me what is the energy to form CO2, then it would be a negative. Is that right?
From to form CO2, the enthalpy of formation would be a different table. It would
Gotcha.
end up being negative because
Okay.
the enthalpy of formation of that is negative. Remember what I said? What is this? Our fourth way of getting at this number? This is all different. We're coming from different directions to get what basically amounts to being the same number. And so I can actually go uh, to a table and I can get delta H of formation for CO2. And it's some number. It's not 808 because you've also got to count for the water. But we could take the enthalpies of formation for CO2 and water, add them up, and subtract off the enthalpies of formation for CH4 and the oxygen, which is oxygen's zero enthalpy of formation. Add them up, take the difference, and what do you got? You'll get a number that's somewhere in the 800s. So this is all just coming at it from different directions is what we're doing. Actually, I think it's actually very comforting that it doesn't matter which direction you come from, you'll get about the same answer. So which one do you use in real life? Well, you use whichever table's handy, whichever one that requires the least steps to cross the lab. You know, that's generally what you do. Okay, does that answer your question? Yeah, it does. Okay, good.
Yeah, it does. It does. Thank you.
All righty. Okay. So that's how you do that. So make sure you're not using double negatives. You're just plugging in the number. So hopefully everybody sees that now. And so I won't do any more examples of this because literally it's like you just got to keep track of what's broken, what's formed. And if you're going to make a mistake, here's common areas to make a mistake if you are going to make a mistake. Right here with the carbon dioxide, common mistake, you just use one, CO. Because you look at the carbon dioxide and you go, it's carbon double bonded oxygen, and you leave it at that, and you say, oh, yeah, I got it, right? But there's two of them. That's not very common, but it is a common mistake. And the really, really common one is to leave off the two here. That's really, really common. Because you'll say, I've got this, I've got this. Water is an OH and an OH has two OH bonds. Yes, I've got this. And then you forget to multiply by two. Okay, so those, and I tell you these things because it's little things you got to watch out for. Just these little things. But they do make a difference. Okay, so let me make sure I hit everything from this chapter, and I did. Okay. All right, well that's chapter 8. Okay, that's chapter 8. Okay, so you got to be able to do this, but it's just another way of getting that delta H reaction, okay? All right. Now, remember what I said? We're going to go right back to these Lewis dot structures and such, because as I said, 8 and 9 really go together. 8 and 9 really go together. So we have this thing called Vesper, which I always end up misspelling. Where's Vesper? I just want to make sure. VSEPR. I always want to make it VES, so it's VSEPR. Otherwise known as, you say it as Vesper, even though it's VS and not VE. But what we pronounce it as Vesper, and it's short for valence shell electron pair repulsion. Very long word. Nobody ever says that. You just say Vesper. All right. And the idea is a Vesper is that atoms want to get as far away as get away to minimize repulsions. That's what Vesper does. You're trying to minimize repulsions. And you may just say to yourself, well, what the heck does that mean? Well, what's on the outside of atoms? Electrons. Electrons are on the outside of atoms. And what are electrons? They're negatively charged. So if you take any atom and put it next to any atom, they're going to see these electrons on the outside, and they're going to want to get away from each other. They're going to want to push away from each other because like charges repel. Okay, so they're going to repel in general. If they're not bonded, they're going to want to get away from each other. All right, so what does that mean? Well, that means that if you have something like let's say our carbon tetrafluoride, and you were to sketch this out, well, you wouldn't see this because these guys would be considerably closer together than those guys. And so the shape that you get is going to end up being whatever minimizes the repulsions. In other words, everybody's as far apart as everybody can get. Okay, so if you were to take something like carbon dioxide, for instance, well, it's this shape right here. This is linear. Okay, because it looks like a line. All right, but look at this. You have, what's the bond angle between here and here? Between there and there is 180 degrees. Now, you can also say, if we move these things like this, then this becomes less than 180 degrees, and this right here becomes greater than 180 degrees. So this is higher energy, so the energy goes up for this. All right, because they're closer. They're closer. And really it comes back to this. E equals some sort of K, Q1, Q2 over the distance, right? You're not changing the Q, but you are changing the distance, okay? So as you get them closer together, the energy goes up. Everything wants to be at the lowest possible energy. All right, so they're gonna want to be, like in this case, they're gonna be with the CO2, they're gonna be one as far apart as possible. Now, these bond angles, and since y'all are sciencey kind of people, these actually represent, this 180 degrees represents an average. This molecule actually wiggles. These guys actually wiggle back and forth. And so this actually wiggles. Let me draw it back over here. This actually wiggles like this. I'm exaggerating, but these guys actually wiggle back and forth. Okay? They're constantly going back and forth like this. They're just wiggling, just flopping. They do this. Okay? And the reason why I say this is don't get fixed on looking at these bonds and saying that they're stuck in this position as if they were drilled into some sort of hole, like some sort of model. Okay? They're not. They wiggle. Matter of fact, remember when we did electronic transitions, right? Didn't we do that where we had like line spectra and all that? This is a vibration. Okay, it's wiggling. It's a vibration, and you can actually see this in infrared. It'll actually show up in infrared like this. You see lines. Just like line spectra. This shows up in infrared. Okay, so it's there. It's real. These molecules are constantly flopping around. Now, the degree they flop around, how many degrees they go up and down, depends on how stiff the bonds are. The more stiff, the less they're going to move. The more constrained they are, the less they're going to move. But they do wiggle. So I just want to make everyone clear on that. Since we're sciencey and this is a science major class, they don't sit there in one position. That 180 degrees represents an average. But on average, they're pretty close. All right, so like this guy right here, this linear was going to flop around a 180, and if we were to take something like boron trifluoride, we would actually end up with something that looks like this. And the bond angles would end up being about 120 degrees. Okay? And we would call this trigonal planar. It's a triangle. It sits in the plane. See the triangle here? See the triangle? It's a triangle. It sits in the plane. All right? And we can actually do things like substitute with lone pairs. We can actually put a lone pair in there. Remember those that we just did? We could put a lone pair in there. And as far as the electronic domain goes, in other words, all the electrons together, it's still trigonal planar. But what's the shape here? Well, this would be bent. It's a bent shape, right? It's like a boomerang. It's bent. But what's the angle here? Still about 120 degrees. You see? Angle from here to there, it's about 120 degrees. All right. We can look at something that's got like 4 things around it, and we go, like this guy right here. And if we do 4 things around this, CH4, God, my H's look terrible. Let me do this here. That's supposed to be this is CH4. Okay. And this is a 3-dimensional structure, so you would actually say one of these hydrogens is actually pointing out of the board. And you would take one of these guys, and we're going to do a dashed wedge, and we're going to say it's in the board. So solid means out, dash means in, and just the line means on the board. It's one of many ways of representing a 3-dimensional object. These guys actually have 3-dimensional shapes. All right. And if you do that, this is a 4-face regular solid. 4-face regular solid. We call this tetrahedral. All right, but it's like there it is. It's got 4 triangle-shaped faces, and it's got 4 points. And the bond angle here, all the bond angles are the same, is 109.5 degrees. If you go around, this is a solid object. Okay, so you may be looking, now you have to be very careful. When we did the Lewis dot structure, what did we get? We went north, east, south, and west, right? And this is where you've got to be careful with the Lewis dot structures versus the actual solid physical shape. Is you would think, looking at this, what would you think? You would think 90 degrees, wouldn't you? But it's not. Okay? It's not, because this is a representation. The Lewis structure is a representation that tells you how many things are bonded or whatever. This up here is the actual structure. This is 3D up here. This is three-dimensional structure. This is just the flat, drawing it on a page to help us try to understand. So it's not 90 degrees, okay? It's not 90 degrees. Now, most people can get past this, but what'll happen is that water molecule, for instance, looks like this. If you do the Lewis dot, you end up with something that looks like that. And you may say that this is linear, but it's not. It actually looks like a better way to draw it is with bunny ears. See the bunny ears? There we go, bunny ears. This is better, and this is the same sort of deal up here. This is 109, 109. Okay. If you looked at this, you might say this is linear. This is not linear, this is bent. Okay, this is bent. All right, so water molecules are bent. All right, and so if we take these things further, we can actually get these compounds that might. Now I'm just going to draw a hypothetical. Maybe it's real, maybe it's not. Let's do. Yeah. So. Hold on. And we can have these kind of guys right here. This is another one. Okay, this is where you've got 3 iodines joined up with a bromine, and you've got these 2 lone pairs off to the side. Okay, and I'm just saying this is just a hypothetical. Okay, and this would actually be, and I'm gonna show you, there's a table, but I'm just kind of showing you some examples. If you look on the plane here, there's an equatorial part and then there's an axial part. So this is axial, this is equatorial, because it's on the equator. And if you were to set this on its side, what would it look like? Would help if there we go. If you were to set this on its side, what would it look like? It would look like a T. See that? All I did was turn it on its side, so that's T-shaped. Okay, so these are the kind of things that we're looking at, is that they're 3-dimensional structures that have shape. Now, where do we find all of this? Where we find all of this is on page 350. Page 350 and 353. We have the shapes. All right, what we look for on our table is we look for bonded and non-bonded. Okay, that's what we're looking for. So if we look here, what do we see here? We see 4 bonded. I see 2 non-bonded. Okay, and I look on my table on page 353 and I see, what do we got here? We got 3 bonded, 2 non-bonded. You see that? If you're looking on page 353, and you will see, sure enough, it says T-shaped on page 353. Okay, now, it is helpful if you can memorize these, but you do have a table in front of you on page 350 and page 353, okay? All right, more on this in a second. It's time. It's almost 11 o'clock, so we should go ahead and take a break, and we'll turn off the recorder. Recording. Stop.